Hello, everybody. Welcome to the last lecture on our nervous system chapter, chapter 12. You're listening to this recording because on the day of this lecture, you took your practical 3. So this recording is a replacement for that lecture that you missed, which was on Wednesday. So in this long chapter of chapter 12, we started out explaining what does it take for a neuron to create a nerve impulse and to move that nerve impulse along. And we started out by looking at the ability of the neuron to create an action potential. And then we followed, that's still in lecture 2, the ways a neuron can move a nerve impulse, sometimes through several feet, to its destination. And as far as a single neuron is concerned, those are all the functions we are asking for our neurons to do. However, in the course of many biological events or nervous system carry out, we need more than just one neuron to work perfectly. I'll give you a couple of examples. Think about your biceps brachii muscle. The nerve impulse to instruct that muscle to contract starts from our brain, from this precentral gyrus, which we'll mention in chapter 14 in a little more detail. And from that precentral gyrus in the brain, nerve impulse needs to go through 2 neurons to get to the biceps brachii muscle. The first neuron goes all the way to the spinal cord, and the second neuron takes that nerve impulse from the spinal cord all the way to the biceps brachii. So another example, which will be coming to us in chapter 15, we'll be seeing that part of our autonomic nervous system relies on 2 sequential neurons to move nerve impulses from the spinal cord all the way to the heart, to the lungs, to the small intestine, and many other targets. So this idea that a neuron needs to pass the nerve impulse onto another neuron is very common in our nervous system. This is the third bread and butter type of action inside our nervous system. And so this is the topic of the third lecture. How do neurons pass a nerve impulse onto another neuron? The structure that's responsible for this action will look very, very familiar, despite the fact that we're calling this a synapse. So synapse is the junction between 2 neighboring neurons. How could this look any familiar to us? Because the structure and many players that we'll be seeing in a synapse will have already showed up in chapter 10. The structures within the neuromuscular junction look very similar, and as you'll see, will act very similar to the synapse. So you see on this slide 2 ways these junctions can act. The electrical synapses allow the action potential, the nerve impulse, to continue directly onto another neuron by allowing ionic flow from one neuron to another. This requires a physical connection between the 2 cell membranes of the 2 cells, and gap junction allows this to do. In the human body, we have very few electrical synapses, so our attention will be focusing on the chemical synapses, where we use a chemical mediator, a neurotransmitter, to take the signal from one neuron to another. And this signal transfer will be very similar to what you have seen in the neuromuscular junction, where acetylcholine was that neurotransmitter. Again, you'll be seeing very, very familiar actions when we look at chemical synapses. Let's see if I can advance this slide right here. So here is the static view of a chemical synapse. For a minute, compare it to the neuromuscular junction. First, here is at the end of a neuron, the axon forms an end bulb, just like in the neuromuscular junction. Take a look at the other neuron here. It forms a dip on the surface, very similar to the motor end plate on the surface of the muscle cell. So even the general look of this chemical synapse have similar physical features to the neuromuscular junction. Let's take a look at the individual players. The nerve impulse, as it's coming to the end of the axon, will trigger the flow of calcium. Okay, we didn't see these, or at least we didn't detail these in the neuromuscular junction. But take a look at these synaptic vesicles. They are loaded with neurotransmitters. We did see them at the neuromuscular junction. So here, in our case, calcium coming through the voltage-gated channels, these calcium ions will force the synaptic vesicles to move to the membrane, and exocytosis will be created here. The neurotransmitter, these brownish-looking molecules, will be shoved into the synaptic cleft, this gap between the cell membrane of the presynaptic neuron and postsynaptic neuron. So the presynaptic neuron is carrying the signal all the way to the end, and then this nerve impulse makes synaptic vesicles to dump exocytose, their content, into the synaptic cleft. On the postsynaptic neuron, we must have ligand-gated channels. So these ligand-gated channels in green will grab onto the ligand, which in our case here is the neurotransmitter acetylcholine. And as you look at this sequence from left to right, you can see that the ligand-gated channel, after binding to acetylcholine, will open up the pore, and sodium ions will rush into the postsynaptic neuron. Now, this movement of sodium ions into a neuron should ring a bell. We have defined the beginning of action potential as the opening of sodium channels, allowing sodium movement into the neuron. So we can say that this action that you see here is nothing else but, excuse me, a depolarization event, the beginning of an action potential, and a beginning of the excitement of this postsynaptic neuron. So once we excite this postsynaptic neuron, we have accomplished the transfer of excitement from neuron number 1, the presynaptic neuron, onto neuron number 2, the postsynaptic neuron. So this transfer of excitement is the transfer, the passing on the signal in our nervous system. So just a few numbers here. The postsynaptic neurons have not only one way to contact another neuron, but on an average neuron, there are about 3,000 of these structures, synapses. So a single neuron can listen to 3,000 opinions, influences before this postsynaptic neuron makes up its mind. Imagine, let's say, before you decide whether you want to buy a shoe or not, you listen to 3,000 text messages, TikTok posts, Instagram profiles, WhatsApp messages, and then you decide. I think none of us have have done this like neurons do, listen to 3,000 separate opinions, but that's the life of a neuron. 3,000 incoming messages, incoming signals need to be sorted out for this neuron to make a decision. And as we'll be seeing it in 5-10 minutes, the synapse not only can excite the postsynaptic neuron, through some synapses, inhibition can be carried out as well. So the job of the postsynaptic neuron is nothing enviable. It's receiving thousands of instructions, some wanting to make it excited, some other are turning this postsynaptic neuron off. So it needs to sort out a lot of these positive and negative influences on it. So from here, let's take a look at the animated version of this synapse. Again, the animation in its style will be very similar to what you've seen in the case of neuromuscular junction. Excuse me. Here is our presynaptic neuron in yellow. The postsynaptic neuron is in blue, and you can see this large dip on the surface of the postsynaptic neuron, giving room to the axon end bulb. You see the neurotransmitters bottled up in the synaptic vesicles. You see the voltage-gated calcium channel on the presynaptic neuron. On the postsynaptic neuron, here's the closed ligand-gated channel, and in the pink spheres are sodium ions just waiting for this channel to open up and move into the postsynaptic neuron. So let's start this animation and let's take a look at the events. So here comes the action potential opening the voltage-gated calcium channels, and calcium ions rush into the axon end bulb. And these calcium ions will start the exocytosis. As you can see here, the acetylcholine neurotransmitter is dumped into the synaptic cleft. This ligand, the acetylcholine, will bind to the ligand-gated sodium channels. And here's the opening of the channel. Sodium ions are now rushing into the cell. Now, remember, sodium ions have high concentrations outside the cell because we have that sodium-potassium pump moving sodium ions constantly to the outside. So there's always a crowd of sodium ions on the outside waiting to come in. And when the ligand-gated sodium channel opens, sodium ions go from a place of high concentration on the outside to the place of low concentration on the inside of the cell. So this is a natural movement of sodium. As soon as we open a channel for sodium, it's going to be moving to the inside of a cell. And of course, this movement of sodium into the postsynaptic neuron represents depolarization, the first event in the sequence of forming an action potential. So in this event that you saw animated here, the postsynaptic neuron is going to be excited. Sodium ions flowing into the cell represent the first part of the new excitement, the action potential. So let's move on to some of the details within this chemical synapse. On this slide, I just want to point out the incredible speed. So the nerve impulse is flowing very quickly through the end of an axon. It goes as far as a foot in every 15-20 milliseconds. So if you think that the synapse would delay the flow of nerve impulses in any significant manner, Think again, the delay in this synaptic information transfer is about half a millisecond. Now think about it. Let's assume that the nerve impulse takes about 20 milliseconds to go from our brain to the spinal cord, and then another 20 milliseconds to go from the spinal cord to the biceps brachii muscle. It's a total of 40 milliseconds. So half a millisecond delay is virtually unnoticeable in this flow of nerve impulses at that synapse in the spinal cord. Also, let's keep this in mind that for human perspective, about 200 milliseconds of time is considered instantaneous. This is how we perceive time. And so that 40 and a half millisecond still remains instantaneous. And this is the speed how we control skeletal muscles. Once we think about a movement from our perspective, it is done instantaneously, such as the contraction of the biceps brachii muscle. The chemical synapse also provides a one-way flow of information. Information cannot flow back to the presynaptic neuron because it has no acetylcholine receptors. So that placement of acetylcholine receptors on the postsynaptic neuron provides this one-way flow of the information. And here comes a little unexpected complication. Let's talk about different types of neurotransmitters. In the neuromuscular junction, we have so easy explanation how the muscle gets excited because we have this acetylcholine as our neurotransmitter. This always causes excitement in the muscle and also in the postsynaptic neuron. Excitatory neurotransmitters are epinephrine, norepinephrine, dopamine. So we have 4 excitatory neurotransmitters listed here. But then some of the neurotransmitters you see here are inhibitory. Glutamate, aspartate, gamma-aminobutyric acid. This is sometimes abbreviated as GABA, GABA, glycine. Those are all inhibitory neurotransmitters. So this opens up the possibility that the presynaptic neuron can pass information onto the postsynaptic neuron that will be interpreted as inhibition. This is a really important note here. In your textbook, there's a detailed table about neurotransmitters in chapter 12. Please look up all those neurotransmitters and the molecular nature of these neurotransmitters. You'll see that all neurotransmitters are small organic molecules like glutamate, aspartate, glycine. These are amino acids. Epinephrine, norepinephrine, dopamine are organic amines. But take a look at the table. There are more types of neurotransmitters listed in that table. In terms of the action of the neurotransmitters, we're going to have further details. And not only the excitatory and inhibitory neurotransmitters justify this expended time on neurotransmitters, but as I'll be showing you in a few minutes, pharmaceutical influence on our nervous system a lot of the times are happening by influencing increasing or decreasing levels of neurotransmitters, especially in our central nervous system. So let's take a look at some of the basic action that happens to neurotransmitters. So once acetylcholine is inside the synaptic cleft, it can cause excitation forever. Well, our nervous system and our neurons need to be ready for a new communication in a matter of milliseconds. So to prevent that continued extended excitation, neurotransmitters are routinely degraded. Acetylcholine is degraded by this enzyme, acetylcholine esterase. Um, uh, Inhibiting this enzyme can allow more acetylcholine remaining in the synaptic cleft. And this is one pharmaceutical, Tacrine, that is used in Alzheimer's disease patients. Some other neurotransmitters are degraded by the enzymes called monoamino oxidase, such as epinephrine, serotonin, are all degraded by this enzyme. And manipulating this monoamino oxidase can be used to treat depression, Parkinson's disease. In addition to enzymatic degradation, especially astrocytes among the neuroglia cells can vacuum out, remove neurotransmitters. And we have some pharmaceuticals that act on these neurotransmitter transporters. So let me show you a table. This is not part of your lecture exam 4. This is just an illustration how well pharmaceutical industry have learned to create drugs to manipulate neurotransmitter levels and just what their effect on our nervous system. So here's this table I put together. Let's take a look at just a few. Think about the condition of the central nervous system we call depression. In general, depression is associated with a lower than normal level of many parts of our central nervous system. So here comes an idea from a pharmaceutical company. Why don't we increase the overall activity of neurons in our central nervous system? How are we going to do that? Well, let's take a look. Prozac, Zoloft, they inhibit serotonin removal from the synapse, from the chemical synapse, and this leads to more excitatory action in our central nervous system. Excitatory postsynaptic potential is increased, and therefore our mood is going to improve because we are increasing activity in some parts of our central nervous system. What about other ways to do this? Another antidepressant, Nardia, is inhibiting an enzyme that would degrade dopamine or serotonin. So there will be more excitatory neurotransmitters in the synaptic cleft. Yet again, we are achieving more excitatory postsynaptic potential. We are increasing activity level in our central nervous system. We are acting against depression. So this is yet again an antidepressant. What about a third one? This is a very unusual way to cause increased level of activity in our central nervous system by inhibiting an inhibitory neurotransmitter with its receptor. So less inhibition translates into more excitation. So we can fight low levels of activity in our central nervous system by several different ways. And if you looked at all these three types of drugs, they're all acting on neurotransmitters: serotonin, dopamine, gamma aminobutyric acid. What happens when our central nervous system is hyperactive? One consequence of a hyperactive and out of control hyperactivity in our central nervous system is convulsions, epileptic seizures. So sorry about this typo here. This is supposed to be anti-epileptic. So how can we lower the level of our central nervous, of the activity in our central nervous system by pharmaceuticals? Again, the answer here is acting on neurotransmitters. Barbiturates or helpers, agonists of this gamma aminobutyric acid neurotransmitter. So helping this inhibitory neurotransmitter will lead to more inhibitory activity in our central nervous system. So this hyperactivity can be brought under control. The overall level of our nervous system, activity in our nervous system will be lowered. What about anxiety? Well, anxiety is another type of overactivity, hyperactivity in our central nervous system. Let's take a look at Valium. We are aiming to lower the level of overall activity in our central nervous system, and Valium does this by making this inhibitory neurotransmitter work better with its receptor in the synaptic cleft. When this happens, we are increasing inhibition in the postsynaptic neuron and therefore lowering anxiety, lowering that unusual high level of activity in our central nervous system. And you can look at the rest of these examples here. Time and time again, our pharmaceutical industry reaches for drugs that influence neurotransmitter level in our central nervous system. So neurotransmitters are not only important for natural physiological action in our central nervous system, neurotransmitters are also the handles, the tools that our pharmaceutical industry uses, targets to change undesirable high or undesirable low level of our central nervous system. And so the outcome of these inhibitory or excitatory neurotransmitters will be either excitatory postsynaptic potential or EPSP, or inhibitory postsynaptic potential or IPSP. To cause excitation in the postsynaptic neuron, all we have to do is open those ligand-gated sodium channels. Sodium ions will rush into the postsynaptic neuron. We have a depolarization event and we have excitation. So this is the mechanism you saw on that static illustration and also on the animation. Now, what about those neurotransmitters that cause inhibitory postsynaptic potential? You've seen that our pharmaceutical industry are using this in several cases to lower the activity of our central nervous system. What's happening there? So if we want to depress or lower the activity of the postsynaptic potential, cause an IPSP, we will have to open ligand-gated chloride or ligand-gated potassium channels. When we open ligand-gated chloride channels, chloride ions, negatively charged ions, will rush into the neuron, cause the millivolt level to go into minus 90 millivolt area. That's caused hyperpolarized, and at that stage, the neuron cannot possibly fire a nerve impulse. So we are inhibiting it by moving chloride ions into the cell. If we are opening a ligand-gated potassium channels, potassium ions will rush out of the cell. And again, the total charges inside the neuron will become more and more negative because we are losing positively charged potassium ions. And yet again, this postsynaptic neuron will become more negative, hyperpolarized, and the millivolt level will drop to the 90s. Very difficult to create an excitation in a neuron where the millivolt inside the neuron is minus 90. So this is the molecular basis of the excitation versus the inhibition of the postsynaptic neuron. This is a great illustration of what this postsynaptic neuron needs to deal with. Now, here in this illustration, we have 5 presynaptic neurons. Again, imagine a neuron that has 3,000 presynaptic neurons bringing instructions to it. So this neuron will have to think the following way. After getting all the 3,000 inputs, do I feel hyperpolarized? Is my millivolt level in the 90s, or is my millivolt level close to minus 55, closer to the threshold? So if the overall millivolt level in this postsynaptic neuron is minus 55, this postsynaptic neuron will get excitation, and a new nerve impulse will be fired at the trigger zone. If the millivolt level in this postsynaptic neuron is more like minus 90, and this postsynaptic neuron will stay quiet and no nerve impulse will be fired, so the inhibition will take place in this postsynaptic neuron. So you see here 5 presynaptic neurons. Even 3,000 presynaptic neurons are mind-boggling compared to this illustration. And then think about the world champion coordinator in our nervous system. In chapter 14, we'll mention a part of our brain called cerebellum. Cerebellum is in charge of coordinating skeletal muscle action. The neurons in the cerebellum has 250,000 presynaptic neurons influencing a single postsynaptic neuron. There's an incredible level of connectedness in the cerebellum, part of our brain. And would you like the job of that postsynaptic neuron in the cerebellum? Now you have to listen to 250,000 text messages, TikTok posts, Instagram profiles, WhatsApp messages to make up your mind, and make it up in a matter of milliseconds. So it's an incredible job that our cerebellum does and the neurons there do to make a decision out of so many thousands of inputs. And so this is just telling you that our nervous system works in a mesmerizingly quick way, creating decisions from thousands and sometimes hundreds of thousands of incoming signals, information. So when we put this all together, the postsynaptic neuron can do 3 different things. When the excitation doesn't quite reach the threshold, the inside of the postsynaptic neuron will remain at minus 56 millivolt. There's no new action potential created. The postsynaptic neuron will stay quiet. If the overall input into this postsynaptic neuron results in a membrane potential of at least minus 55 millivolt, then we are crossing the threshold into forming an action potential, and this postsynaptic neuron will create a new action potential and nerve impulse. And the third possibility is that when the millivoltage drops below minus 70, typically to the minus 90 area, then this postsynaptic neuron is hyperpolarized, and the overall input caused this postsynaptic neuron to remain quiet, not to fire an action potential or nerve impulse. In our nervous system, there's quite a bit of room for inhibitory activity. You'll see the first action actually causing an inhibition in chapter 13, where we'll be talking about reflexes. But if you think back to chapter 11, we mentioned the coordination between muscles. Think about this. If you want to contract your biceps brachii muscle, that neuron that goes to the biceps brachii will have to be excited so it can deliver an action potential. But by the same token, the oppositely acting muscle, such as the triceps brachii, will be receiving an inhibition, and the neuron that takes nerve impulse to our triceps brachii will be hyperpolarized. This will prevent the action of the triceps brachii while the biceps brachii is working. So that coordination, the antagonist muscle situation that we described in chapter 11 is the outcome of the excitation sent to the prime mover, such as biceps brachii in our example, and inhibition sent to the opposite acting muscle, such as triceps brachii in our example. Again, a little more of this EPSP versus IPSP will be on display in chapter 13. So I hope this recording was informative enough so you will be well prepared for the lecture exam 4 coming up next week. Please let me know if you have any questions. I'll be attaching this recording and sending you a message through your class shell. If you have any questions, as usual, please don't hesitate to ask me. And I'm going to close right here. I hope you guys have a great weekend and a great preparation for lecture exam 4.